Good afternoon. Thank you for inviting us. We are from Group Álava. We are a group of enterprise, and we become from Álava Ingenieros and Team So2. And our goal or passion is connecting the industrial world with the digital world. About the presentation, we are going to start talking about computer vision, its application in all the spectrum, and how important is artificial intelligence, focusing that in the data and in the deep learning. What about computer vision, which is its aim? The aim of computer vision always is to replicate the human visual system in the objective of this ease of synthesis and analysis. This is a way to extract all the information about our eyes is watching. But we have a limitation in our human visual system, and it's we just see the visible range. But the computer vision one is the domain in the whole spectrum, not just the visible, the infrared spectrum too. And finally, there is a sentence that explains everything in the computer vision, and it's a picture is worth than 1,000 words. Is the way that you can get a lot of information from an image. It's all data. Get as much information as possible. So the computer vision system is equal as the human visual system, as we can see. We can split in three components. The first of all, the capture part, the camera, is for eyes. Then the connection, protocols, wiring, communication, or neurons. Finally, the brain, the intelligence, the artificial intelligence. This is the deep learning algorithms, the computer vision libraries. So we will focus our presentation. Daniel is on the part of the brain, and in my case, on the eyes, the capture. Now I'm going to show you some applications. In all the infrared spectrum, we need this intelligence that we are talking about. Here we have an application of defects in solar panels. This is on the night, and how it is done, because all is dark, and if you go in the fields, you can't watch nothing of the defects in the panel inspections. But with the electrolumininity supply, which human eye is not sensitive, we need a camera with a gas sensor. We need this information from visible to the stereo spectrum, as you see, from 400 to 1,700 nanometers. And then we can get this kind of images that, as we see, yes, we can see the defects, but it's not easy as we see normally and in the first view, because it's not a controlled environment. Normally, the operator is in movement, so we don't have a controlled environment of the same position. It's not a fixed shape of the same defects, and we ignore which is the green intensity of the defects. In addition, we have multiple types of defects and two kinds of material inside the panel, in the solar panel. Sorry, the monocrystalline and polycrystalline. So it does very different defects. A common example in industry is the search for thermal contrast, which indicates on a surface with a similar temperature a defect. At first view, it seems very easy to find this defect. In this image, this has been captured with a rear camera of a thermographic camera. If we inspect the image, what we will see is we have a very low contrast of temperature. Really, the high temperature that we have is provoked by the reflections. The reflections what give us is false information and incorrect information. So we have too much problems in this kind of applications. Noise, low contrast, reflections, the uncontrollable base, as we see in the graphic. Finally, the low resolution per defect, because as you see, it's very small. Finally, I show you a case of a study from our major partner of an application of sorting the cell smasher based on shell fragments. These kind of images are from X-ray images. So this is very important of how we are capturing this data and then how to process that. This is something that my colleague Daniel is going to explain you about deep learning application in computer vision.
Well, why and when we need deep learning in computer vision? When we have complex problems which cannot be solved using threshold or known image feature detection methods, we need more complex methods that learn complex filters and feature extraction methods automatically to solve our problems. And this is only possible when we have lots of available data that we can learn from. So when we have a complex problem and lots of available data, deep learning is the best option. What are the advantages of deep learning approach? The advantages are that the algorithm is there, the best feature extraction method, and we can achieve a state-of-the-art performance in most complex problems. And the main disadvantage are that we need powerful GPUs to train the models, we need deep learning developers, and we need large dataset or good data simulation augmentation technique to be able to solve that kind of problems. As we can see in this image, we are comparing a traditional computer vision data pipeline and a deep learning pipeline. So here we have a process where we do feature engineering manually and start the features and input it to a classifier. And in deep learning, we let the algorithm to extract the feature from the data automatically. So we can extract better features and with less effort and cost. What kind of problem can we solve using deep learning applied to computer vision? Well, the main problem are classification, segmentation, regression, and generation. Classification, we have input image, and we want to classify them in some fixed categories. For example, we have an airplane image, and we want to classify the airplane state. In segmentation, we want to know where the objects are or parts of them in an image. We can do it pieces-wise with segmentation mask or using bounding boxes. So in this image, we see how we color different every object depending on its kind, and how we have here a fully convolutional neural network that we will explain later that does this process of generating those segmentation marks to locate the image the object in an image. And with regression, we can obtain some numeric metric, for example, how a machine part has iterated. And using generation, we can generate new realistic image using deep learning. We have traditional data augmentation techniques that can flip and rotate image, and that may help to train deep learning models. But the deep learning tools to generate image are even better and can perform style transfer, generating new realistic image from random noise. And here we have, for example, how we can convert Monet picture into real photos, zebras to horse, a summer landscape into a winter landscape, and how this is very useful when we have imbalanced data sets and we want to rebalance it to train better models. For example, we are studying matching failures, and we have a lot of data of the matching working correctly, and very few examples of the matching being broken. And can we apply those techniques in hyperspectral imaging? Yes, we just have a bit more complex input data. In this case, we see a hypercube, but the process and the algorithms is the same. Because of this, it's common to perform simple initial feature extraction like HYPERSPECTRAL vector, dimensionality reduction before using the algorithm. Here we have a hyperspectral image of a satellite image, and we do some technique to extract subcubes, spectral vectors, or performing dimensionality reduction after that something spatial cube, spatial vectors, and that using as an input of some algorithms to classify, in this case, the type of surveys present in the hyperspectral image. Now, we are going to explain what are the most common algorithms that we use in deep learning to perform those mentioned tasks. So the most important ones and the most used ones are the convolutional neural networks that are based on automatic feature extraction, which we call convolution. And we can see in the left image, we perform the filter on an image in the sample network, and then dimensionality reduction that we call pooling. For example, one type of pooling is max pooling, and we can see in the image too how we do some filtering in an image and then do this max pooling to reduce its dimensionality. And we use these methods to get an information that we can pass a fully connected network to perform a classification or regression task, or to re-amplify the network, and we can see in the right example to generate, for example, segmentation mask and an output image. So the important part of this network is that this convolution, these filters, are learned automatically. So there is no necessary to perform feature engineering, manual feature engineering by a person doing the filters. A very useful algorithm is autoencoders that are used to perform the dimensionality reduction and also to filter noise, that the two main uses. And they have an encoding process where they reduce the image to its compressed state, and then an encoding process where they re-amplify the image and try to reconstruct it from the basic data. They perform much better than a dimensionality reduction method like PSA or DSNA. For example, we see the original image and the reconstruction performed by autoencoder and by a PCA, and we can see that autoencoder reconstruction have much higher quality. And we previously talked about generative methods. The main networks that I use for this data generation are the generative adversarial network that are very good generated neuralized image. They have a latent space of all the possible image in this universe, and they are able to generate new image for random noise or performance type transfer or other data generator tags. They are composed by a generator and a discriminator, two networks that compete with each other. The generator generates new image, the more realistic as possible, and the discriminator tries to distinguish between the image generated by the generator and the image that are real samples. And when the generator is able to fool the discriminator, then we can say that the network is correctly trained and the sample must be very realistic. We also have custom network. Custom network are a new revolution in artificial vision because these networks are aware of the perspective and the relative position of the objects. So they are like convolutional neural network, but they use capsules that are a group of neurons and pass this output for high dimensional capsules, and they encode the probability of observation and the pose. So, and they discard the pooling process. They don't make dimensional reduction. So, for example, we see a face in this image and we see that we change the order of elements, and the left one is a phase and the right one is not a phase. For a convolutional network, because all the elements are present, both will be phases. But for a capsule network that encode the pose and encode the relative position of the elements in the image, the left one would be a phase and the right one would not. The same is with the perspective example we see with the Liberty statue, that and convolutional network would be will need a lot of samples to see that this is the same object, but the capsule networks are not able to understand the perspective. And finally, we have the recurrent neural network that are not directly used in artificial vision, but they are very good dealing with sequence data, with time series data. So they are usually used in combination with convolutional neural network to process videos. We use the CNN to extract the features from the video, and then in this case we use a STM, that is a type of recurrent neural network, to understand the temporal sequence of those events, those information state extracted by the CNN. So we can understand a video in its time progression instead of frame by frame basic, without taking into account the video as it is. So we here at Grupo Álava, we provide technology that contributes to social development. Thank you very much. For more information, here you have our contacts. We are Daniel Martinez Garcia and Natalia Mira from Grupo Álava.
Thank you very much, both Natalia and Daniel, for your talk. I see here one question from Carlos. How do you train your system? What do you use? I think this is a super general question. So maybe you can just comment on what sort of algorithms do you use for, I think you already talked a bit, but what sort of algorithms and platforms and data that you use for training your system?
Well, it depends on the problem, the kind of algorithms and things like that. But usually we use TensorFlow, we use also PyTorch, we use Keras, we also use Matrox software when we have Matrox cameras. So we use a very high amount of different techniques and framework, and also the algorithms that we use are what we explain in combination with others in complex systems that interact among them. So that's what we use more or less.
Okay. So really state-of-the-art, let's say, platforms, as I can see.
Yes, that's it.
Okay. Okay. Great talk. Thank you very much. I see one more question here. So, how do you evaluate if adding more dimensions in the case of hyperspectral imaging works better?
I will leave this question to Natalia because she's the expert.
Sorry, could you repeat, please?
Yeah. So you have it in the chat as well. So the question is, how do you evaluate if adding more dimension works better? This is for the case of hyperspectral imaging.
For example, when I explained on the thermographic camera about we need more dimension, the spatial dimension, it's because if we measure with thermography, we need always more than 3 pixels to do a good measure. And in fact, in the most of the projects that I did, it is recommended always to have minimum 5 pixels per artifact or defect, or something that you want to affect.
Okay, I see. I hope that this answers the question. And there is one last question from Asier Vicente. Is also Álava providing software solutions as service?
Yeah.
Okay.
Yeah.
Of course.
That's a fast answer. So I guess that you can make tailored solutions, right, for applications. And I guess that if someone has a particular interest, can be in contact with you.
Yes, of course. Now we are going to leave our contact that you have here in the presentation.
Mm-hmm. Okay, so as I said, also this is going to be uploaded, so you can any of the attendees can be in contact with you if they have any questions. So thank you very much.